The choice between belt or string-driven linear slides on your robot can make or break its performance. Yet many teams are relying on random Reddit threads or institutional knowledge passed down from yesteryear. Today, we're ending that guesswork. You're about to see exactly how these two popular systems stack up, finally answering if strings are truly faster and if belts are more reliable, and more importantly, if those differences actually matter for your robot's performance, so that you can build faster, more reliable robots that win. I'm Coach Pratt, and with over a decade in robotics education and having coached FTC teams to national championships and Inspire Awards, I've seen what truly works under pressure. In this video, I'm going to run you through a series of head-to-head experimental tests using some Misumi SAR 330s. We'll put belted and string-strung setups to the test at various motor speeds, and with incrementally increasing 500-gram loads, compare their weights and their speeds, and I'll give you some clear recommendations on which system is best for your robot and why. For the sake of thoroughness, it helps if we weigh both these systems. So let's go ahead and get a baseline for what the system looks like on a strung system. Now I've got a little bit of hardware on here that I need to add up because I don't have that hardware currently attached. I've just added all the pieces that it needs that you would need to be able to hook those up together so we do get a somewhat accurate, well, very accurate point. We'll put all the string that is needed. This is a string I've taken off and I've used in the past. And then our pulley and so on. So we're looking at the weight of our fully strung system is 753.6 grams. Let's go ahead and compare that to the weight of a fully strung system here. Now on this belt system, I have all of the correct hardware already inside. So we'll see what this ends up weighing. Looking at 767.4 grams. So you're looking at about a 10 to 13 gram difference. So the difference you're looking at, Future Pratt, I've forgotten how much this strung system weighed. What's our difference?
13.8 grams.
Okay. Not a lot of difference between these two in terms of weight. And even if you were to stack up two of these, you're looking at double whatever that difference is. So 20 to 30 grams. That's effectively nothing. Another point inside of this test is that the circumferences I'm using are slightly different between the two. So the circumference of our belted system is 37.5, whereas the circumference of our system is 34.5. So there's about 3 millimeter circumference difference between my pulleyed system on the strings and the belt system here, which means this one is going to rotate about 8% faster than this one will. Now that assumes this one is rotating a little bit slower, but if you were to increase the speed of this and increase the size of the pulley, you are also going to directly decrease the amount of torque that it's outputting. And we'll see through some of these tests whether that actually makes a huge difference or not. In the end of this, I'm also going to include two charts. I'm going to include one chart that has the standard pulleys here as their actual measured size. I'm going to include another chart that has some adjusted calculations based on the size difference between these pulleys, with a little bit of wiggle room applied for those torque forces as well. So we should have a pretty accurate design between these two and a pretty fair comparison. Looking at the mechanical setup here, I have 3 Misumi SAR 330s connected together on a continuous rigging. On the extension and retraction string are running on the same adapter. Next is pulley. I've got a 1-to-1 gear ratio using some acetyl gears so that when I go to replace the motor, I don't have to actually replace the pulley and restring my slides every single time. On the top bar here, I have a quick little bar here with a few different zap straps attached so that I can grab weights of different sizes. These are 1 kilogram weights and the small ones are 500 grams so that I can move up in 500 gram increments and load that somewhat balanced across my system as we move up and down. I have 3 Misumi SAR 330 slides. These are the 3-stage systems hooked up here on a belt-driven system. Down on the motor mount itself, I've got a couple different idler bearings to be able to stop this pulley from coming off. On the electronic side of things, I've got a microcontroller here running CircuitPython that has an encoder on the back of the motor so we can keep track of where our top and our bottom sections are. I'm going to have a 2-button switch that's going to be running this, and the motor itself is going to be running off of our 2x30 amp RoboClaw controller here. I'm running it off of an FTC legal 12-volt battery pack here, so you know that the voltages we're running here should be directly applicable to our current system. On the main system itself over here, I have 2 LEDs on our screen. 1 LED placed up at the top, that is green. 1 LED on the bottom, that is yellow. The green one will light up when it is starting its extension. When it finishes, the green light will turn off, and then the yellow light will then turn on. It'll start its retraction, where the yellow light will then turn off at the bottom of that. And we're going to keep track of our cycle times over time on our computer here with the serial output from our board using that encoder. Couple things to note, I'm going to be making sure I'm running a fully charged battery every single test so we get accurate results all the way across, as well as making sure the voltage is consistent across batteries. We'll run each test a couple different times, and we'll see by the end of this, realistically at different weights all the way up, how fast some of these motors are capable of doing things. So let's go ahead and get started. All right, so we've got a fresh battery installed. We're now looking at the 435 motor, but we're going to do the dual strung method. Let's go ahead and get a baseline and see what we're looking at here. Okay, looks like our baseline is about 2.07, 2.075. Let's load up 500 grams and see what that does. Okay, we're looking at about 2.1 seconds on 500 grams. Let's go up to a kilogram and see what that does. Okay, we're looking at about 2.12 on average with a kilo. Let's move up to a kilo and a half. And we're averaging about 2.21 seconds on a kilo and a half. Let's move up to a full 2 kilograms. Ooh, 2 kilograms, you really start to hear this thing struggle. It's sitting about 2.36, 2.32. Let's do one more to get a little more consistency. Okay, 2.31. So let's call that about 2.32. Let's move up to 2.5 kilograms. See what this goes. We're going to do this one once because it's really starting to struggle. And you're sitting at about 2.53. And let's go up to the full 3 kilograms. And you're sitting at about 2.88 on the full 3, and you notice it was really struggling to even hit that top point on the extension as well. So definitely would not recommend 3 kilograms on this dual strung system. Let's go ahead and check out the next motor. So let's go ahead and get a baseline and see what we come up with. So it looks like our baseline is looking at about 2.02. Let's load up 500 grams and see where we go with that. Yeah, baseline about 2.08. Let's move to a kilogram. One more. Hey, you're getting a baseline about 2.16. Let's move up to a kilo and a half. Okay, let's see what a kilo and a half does. We're sitting about 2.21 as the cycle time. Let's move up to a full 2 kilograms. Ooh, we're starting to struggle a bit now. Yeah, 2 kilograms, look about 2.35, 2.36. Let's go to 2.5 kilograms. Ooh, really struggling at this point. Okay, we're looking at about 2.5, 2.51. Let's move up to 3 kilograms. Oh, still lifting up 3 kilograms, but I don't think realistically you're going to get much speed out of that. 2.72. Let's go to 3.5. You're still lifting 3.5 all the way up at about 2.98. That's pretty impressive. Let's go ahead and load up 4 kilograms. This will probably be our last test at this point. And you're sitting about 3.34 as a cycle time of 4 kilograms. So now let's take a look at the 1150 RPM motor with a high quality bearing on the dual strung system. So let's go ahead and get a baseline here. And it looks like your baseline of about 0.74 roughly, 0.73 perhaps. Let's go ahead and load up 500 grams. And let's see what we get on 500 grams. Okay, we got 500 grams loaded. Let's go ahead and take a look at what this does. Okay, we're looking at about 0.79 on average. Let's go ahead and load up a kilogram and see what that does. All right, so we've got a kilogram loaded up. Let's go ahead and take a look at a kilogram system. Okay, I'm only going to run that kilogram once just because it does not like slamming down on about a kilogram because I'm only supporting this on one side. Let's go take a look at the next motor to test. All right, so let's take a look at the final motor in the test here. This is the 1150. So let's go ahead and get a baseline. Looks like we're baselining at about 0.85, 0.83, somewhere in that realm. Let's say about 0.85. Let's load up 500 grams, and let's go ahead and get a baseline at 500. Okay, so let's go ahead and get a baseline at 500 grams here. Looking at about 0.93, upwards of 0.96, so let's say put 0.94, 0.945. Let's go ahead and load up a kilogram and see what that does. Okay, so we've got a kilogram loaded up, so let's go ahead and see how this performs. Okay, we're looking at about 0.11, 0.13, so let's say about 0.12 on a kilogram. This is already looking a lot more consistent than when we had our string slides moving up about a kilogram. We can hear that things aren't really working as hard on this one. So now that we've got all the data across all of our motors, I think we're going to stop out at about a kilogram. I'm not sure. Well, let's try 1,500. Alrighty, so we got about 1,500 grams loaded up on here. Let's go ahead and see what our cycle times are. Whew, that's real slow. And we're sitting at about 1.48, 1.51. Let's go ahead and say about 1.59 or 1.49. Go ahead and stop at 1,500 grams. I think it's going to max out for our motor there. And at this point, we're now done with all of our tests, the 1150. So let's talk about how they actually break down the difference between the two. Remember, when you look at the weight between these two systems, you're talking about a 10 to 15 gram difference between the two. Also remember that when I tested these, at the start of the video, I said that I'm using a different circumference. The belt had a 37 millimeter diameter, whereas the pulley had a 34 millimeter diameter. So that means that our calculation is going to be a little bit different. So what I've done is on the 435, I've adjusted from about 8% down through about 1%, because as we are increasing the load on that system, we're not able to apply as much torque. So it's not a perfect calculation in that technically in a perfect world, it would be an 8.83 times, or it would be 8.83% faster. However, that assumes that the torque that applies on the system is perfectly linear across. So what I've done is I've just made a bit of a linear calculation here. I've taken 8% of the speed adjusted for the 435 motor on a no load system, 7, 6, 5, 4, 1%, and then no change once we hit that sort of overloaded system here. So practically speaking, what kind of difference are we talking about? I'm going to use the adjusted systems here. And then on the 1150, I've adjusted from 7% down to 3% because it requires a lot more torque to get that one up and going. So these are tested on the best case scenario strings. I have a string as my dual strung system, string on a floating string system, both using high quality pulleys. And they ended up being realistically the same. So let's look at the 435 motor because we're looking for absolute speed here. On the belt is in green, the floating string's in purple, and the blue string is in dual. So we'll go ahead and look at the best case scenario, that floating string on the purple. Now you're looking at 1.9 seconds versus 2.02 seconds on a loaded system. You're talking about 0.1 second at this point, 100 milliseconds. That is effectively no difference. And that does not change all the way up through the system. In fact, the belt system performs better under higher loads than a string system does. You say, why is that performing that way? Well, strangely enough, even the string has a smaller circumference on its pulley than the belt did. So the string should actually be doing better than the belt does, especially on these tests. But there seems to be a better force transfer for the belt across more teeth, and perhaps there's a better force transfer across its pulley to be able to grab it. But in any case, the belt is able to lift higher tensions. The belt is able to lift higher weights faster. And practically, there's not a huge difference at the 435 motor. So if you're going to use 435s in your motors, when we're looking at a 20 gram difference between these two systems, realistically, my recommendation would be moving towards belts. But let's see if that changes when it comes down to that 1150. So on 1150, non-adjusted, you're looking at 0.68 on a floating, but realistically, nobody's running this thing's no load. So let's look at 500 grams. You're looking at 0.74, 0.79 on that floating versus dual system, and your belt's about another 0.2. Again, we're talking about 200 milliseconds. Formula One race car drivers barely have that reaction speed, depending on who it is you talk to, from 100 to 300 milliseconds. So let's go ahead and look at these adjusted numbers. I've adjusted 7% at no load, 3% at 500 grams load, and none at 1,000 grams, because there's a pretty steep increase in that curve when we start to get 1,000 grams. So I am effectively saying there's going to be no difference between those two in my calculations because of the increased torque load when it comes to that. Now, again, it's crystal clear. String is faster than belts. However, how much faster, and does that actually matter? You're looking at 0.63 to 0.85 on no load. There's no point looking at a no load system here because nobody is running these things with 0 grams on an implement when it goes out. So let's look at 500 grams. 0.72 on a best case scenario versus 0.94. That is 220 milliseconds as a difference between the two. Does that actually matter? Yes, absolutely on paper, much, much faster. But the benefit that a belt system provides is that they are so much more reliable. They're so much easier to maintain. The braking strength of that belt versus the string tends to be a lot faster, or not faster, tends to be higher. Sorry. The ability to build a belt system versus a string system is a lot easier. You need to buy the specific cord, typically Dyneema or UW HMPE cord, something like that. It tends to be quite expensive. So string could be a little bit cheaper to build, but if you're going to be using a string that doesn't stretch, that's a big one. It's much easier to tension a belt system than it is to tension a string system. A lot of teams use zip ties or zap straps to tension their string systems, and getting exact tension between the two sides is a little more challenging compared to on a belt. It's a little bit easier to get that challenging. So yes, overall strings are absolutely faster, but does that speed actually matter? I think you're going to have a hard time arguing that 200 milliseconds makes a meaningful difference between these systems. So let's do some quick calculations here to see realistically if that 200 millisecond difference is going to make any meaningful change. So let's say that your game is 180 seconds long. And when we look at top performing teams into the deep season, if you were to get every single game piece into that bucket, you would have game pieces scored. You're talking about 20 pieces. Now, if we were to just look at the retraction time that it takes to be able to do some of those. If we're looking at the best case string, you're looking at, let's assume we use 500 grams of load here. You're looking at 0.72. Or 0.72 is the best case string. And the best case belt, this is at the 1150 motor. This is at the 1150 motor. Your best case belt at 500 grams was 0.94. So if we're looking at 0.94 cycle times over gain pieces scores, you're looking at 18 seconds versus 14.4 seconds. So add that all up, and you're talking about an extra 4.4 seconds over the entire course of the system. That is the best case scenario. Now, this assumes that you're not going to add up those seconds across when you're driving across the system. Let's go ahead and look at the 435 best case string, best case belt. Again, we're going to look at those adjusted times. So we're going to say 1.94, 500 grams for the string, and 2.08 for the belt. And again, we're going to go ahead and assume that this is across this. This is across this. So the differences you're looking at are really minimal. Oops. Yeah, I know. So you're looking at 4.4 seconds across and 2.8 seconds across on a best case scenario for the belt. So yes, they are definitively faster. Is that going to make a practical difference? Typically, it takes some time for your robot to move from where you are placing the game piece to where the main system is. And it's not like that is just wasted time where your robot is not moving at all. If you want my recommendation, at least on my setups, I can't see any reason why you wouldn't want to go with belts. They're so much more reliable. Tell me what you thought of the test. If you think it's accurate, what is your experience working on strings versus belts? And have you taken those time to look at those differences quantifiably? If you found this helpful, consider giving it a like. It takes me a long time to make these experiments up, and it really does help the channel grow out so I can make more content for you out on this. And best of luck on building your next robotics project.